How do surface codes correct errors in quantum computers? Imagine trying to keep a delicate message safe in a busy, noisy room. That's similar to what quantum computers face when protecting their fragile quantum information. Surface codes are a clever way to do this. They encode a single logical qubit into a grid of many physical qubits arranged in a two-dimensional pattern. This setup allows the system to spot errors without directly measuring the logical qubit itself, which would cause it to lose its quantum state. Instead, the system measures special multi-qubit operators called stabilizers. These stabilizers check the parity, or the evenness and oddness, of groups of neighboring qubits. If errors happen, these stabilizers reveal patterns called error syndromes, which tell us where something went wrong. The system then uses a classical computer to analyze these syndromes and figure out the most likely errors. Physical qubits often experience bit flip errors, where a 0 turns into a 1, or phase flip errors, which change the quantum phase. The surface code detects these errors by noticing changes in the stabilizer measurements. Because the qubits are arranged in a two-dimensional lattice, errors tend to form chains or loops. The decoder then pairs up the error syndromes to correct these chains, minimizing the chance of a logical error slipping through. One of the biggest advantages of surface codes is their high error threshold. They can handle physical error rates of about 1% and still keep logical errors very low as the lattice size increases. The larger the lattice, the better the error correction, because it makes it harder for errors to form indetectable chains. Recent experiments, like those by Google Quantum AI, have shown that surface codes can correct errors below this threshold. This means logical qubits encoded with surface codes can outperform individual physical qubits in resisting errors. This progress is a big step toward building reliable, large-scale quantum computers. Surface codes also allow logical operations to be performed on encoded qubits without collapsing their quantum states. They do this through special sequences of physical qubit operations, including techniques called transversal gates and lattice surgery. In simple terms, surface codes work by turning a big grid of physical qubits into a resilient shield for quantum information. They detect errors by measuring stabilizers repeatedly, interpret these measurements with classical computers, and correct errors by exploiting the topological properties of the lattice. Increasing the size of the lattice makes the system even better at catching and fixing errors, bringing us closer to the goal of fault-tolerant quantum computing.